Good morning. Do you able to see my presentation?
Yes, sir.
Okay, thank you. Let us continue our discussion. So we are discussing the programmable calculator. Initially, we have seen that in case of simple calculator, so it's only the operators and the integer constant which was being considered. In case of programmable calculator, we incorporated the identifier, and since identifier is incorporated, so related to assignment of some value or integer constant to the identifier is also incorporated as a production rule. Also in this programmable calculator, we are incorporating the possibility of having multiple line expressions. Now today we will finish this discussion by looking at the situation that a programmable calculator, even it is ambiguous, but we can resolve that ambiguity using the help of Bison. That is one of the primary reasons why Bison is so powerful. Now regarding the ambiguity, yesterday we also discussed that ambiguous grammars are with less number of states, and hence the size of the parsing table will also reduce. For this simplest grammar also we have seen that we can reduce few number of states if it is ambiguous grammar. Now where is the ambiguity? Ambiguity is here. So which one to choose? When the expression is of the format E, a binary operator, and E. Now the binary operator can be addition, can be subtraction, can be multiplication, can be division, right? Now for the moment, if I assume that all the operators are with the same precedence, then probably I am on the safe side. Then also I have to mention that associativity doesn't affect. So if I consider that precedence wise and the associativity wise, I have no restriction if I assume that, okay? Then you know how to implement this grammar using Bison. So corresponding to each production rule, so you have to write say else for L statement list colon, then statement list concatenated with statement followed by within single quote /n. Like that way you can write all the 12 production rules. Okay, the same thing I wrote here. So starting from here, so you start looking in between this. So statement colon statement /n, statement list statement, these two are two production rules, 1 and 2. Then name equals to or id equals to E, corresponding to that $1 redirects to value equals to $3. So these things we have discussed on the last class. This is same. The implementation is Bison is same as we have done on yesterday. Only the non-terminals in the production rule has changed. Accordingly, the text in the Bison program will also change. Okay. Now, how I can able to deal with the precedence and associativity even for this ambiguous grammar, even for this grammar where E can produce either E plus E or E minus E or E multiplied with E or E divided by E. So how I can code that one in Bison? That will come in this region. Please look at this region. So here you can see that percent left space within single quote addition space within single quote multiplication, then percent left within single quote multiplication. This is star, although it looks like dot, but actually this is star, space within single quote division slash, next percent non-ASO space u minus. So in order to interpret this one, let me go back to the previous slide. How many operators are there? One, binary addition, binary subtraction, binary multiplication, binary division, and unary minus. So these 5 operators are here: addition, subtraction, multiplication, division, and unary minus. Now to differentiate between binary minus and unary minus, when for the binary minus I am writing within single quote hyphen, but for unary minus I am writing u minus, and I am defining this u minus, as you can see, that all capital, indicating perhaps this is a defined statement. Yes, it is. And I am defining this one in parts.h, that I will show you later. So these 5 operators, addition, subtraction, multiplication, division, all are binary, and one unary minus. Now the percent left here indicates that addition and subtraction both are left associative, so is multiplication and division, and for the unary minus there is no associativity attached. So I am coding that one. I am writing that one in my Bison program. So that way I solved my associativity problem. So although the grammar is ambiguous in nature, but I am telling that, okay, if it is addition, subtraction, multiplication, and division, then it will be left associative, and if it is unary minus, then it will be non-associative. Then what is about the precedence? Bison suggests in this area, in this region specifically, if you provide the associative information like this, then the operator which will occur at the end of this region is with the highest priority, and priority reduces if you go up, or otherwise if you go down, then priority or the precedence is the correct word in this context, precedence increases. If I say that, then you can see from here u minus is with the highest precedence. Next is multiplication and division. Next is addition and subtraction. Okay. Now, if I provide the precedence and the associativity information as a syntax in Bison specification, then I am done. Then if I work with the say ambiguous grammar, then also I have no problem, right? So that is the modification we have done here in order to accommodate the ambiguous grammar. So this part we incorporated, and since u minus is there, so here you see that in this case there is also a change. Now what is the change? Again, to differentiate between subtraction and the unary minus, although I mentioned their name separately here, but here I am explicitly mentioning that percent precedence u minus. So when you will see the reason, you see that here also there is a hyphen, here also there is a hyphen inside the code. Now this indicates binary subtraction, this indicates unary minus. Now when both will occur, then who will get the precedence? For that I am writing this part. Okay. So what is the extra in this Bison program? What is the extra because of the use of the ambiguous grammar with respect to yesterday's class is only these two regions, here and here. In total you can think of 4 lines of code, and that's it. Okay. Now with this, if I proceed, then at the symbol table level there is no change because I am not dealing anything with the extraordinary symbols. It is same as the previous one. Now few notes on those use. Why shall I go for ambiguous grammars? First of all, intentionally I may not wish to go for ambiguous grammar. But incidentally, if you came across to some ambiguous grammar and you need to implement that one, or you need to design one parser based upon that one, then choose the Bison programming language, and instead of making that grammar unambiguous, if the ambiguity is of this nature, then you incorporated that information into your Bison code. Sometimes ambiguous grammar is used for its ease of specification of language. It's of a shorter and more compact representation, lead to less redundant steps during parsing. Introduce some shift-reduced conflicts in the LR parsing, and conflicts are resolved by precedence and associativity of operators. That you can understand. Say if I have one expression, say 2 plus 3 multiplied with 4. Right. Then which one will take precedence? This multiplication will take precedence. And that problem, I mean, after reaching this position, when dot is at this position, then the question is whether I will reduce 2 plus 3. I mean, I will evaluate 2 plus 3, or I will shift to the next after the multiplication. So that as of now we were discussing or deciding based upon look ahead information. Being Bison as a LLR1, so it also has some look ahead information, but apart from that one, when I see that okay, one multiplication and one addition is there, then quickly I will look at their precedence. That precedence information is provided here. Okay. Now going to that slide, using this precedence information, I will decide. And as I mentioned, percent left is used to specify left associative operator. Similarly, percent right is used to specify right associative operators. And if it is without any associativity, then percent non-associativity is used. Also, please remember that precedence is specified by the order of left, right, or non-associative definitions. Later in the order, higher the precedence. Or if I go down, then the precedence increases. However, at each level, all the operators are with the same precedence. The difference for such cases like multiplication and division are with the same precedence. Addition and subtraction both are with the same precedence. Then the discrimination that I need to do is basically using the associativity information. Okay. Now regarding the unary operation, as I mentioned, that there are two different occurrences there can be for hyphen or minus, one as a binary, another as a unary. So you can see that this is a clear case of operator overloading kind of thing, where the meaning is different based upon the context, where it is, how many operands are there. So based upon that one. Good news is that for this unary and binary operations, their precedence information is different. So that's why to discriminate between these two, instead of say, so for binary we are using like addition, multiplication and division to keep the parity with the existing one. Within single quote it is the hyphen, but for unary operation, unary minus, we are naming it as Q minus. Okay. And at the rule section that I pointed out, that this percent precedence U minus is entered. The reason is that, look, whether I am writing say x equals to a minus b, or I am writing say x equals to minus b. So the scanner, what it will do, it will identify this as one token identifier, this is 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 one token identifier. In this case, this is one, this is one, this is one, and this is one. Right? Now you see that in the first case, the subtraction is binary operation. In the second case, it is the unary negative operation or unary minus. But at the scanner level, in both the cases, it is returning hyphen only. What will be the meaning of that hyphen? You can able to understand if you look at the context. So first time we will catch that kind of scenario when we will be doing the parsing. Okay. And Bison also is capable of, right now we modified, we entered the priority and associativity or precedence and associativity information. Now Bison is capable of discriminating between these two minus or subtraction. Okay. Now as I mentioned that U minus is here in the header file. And you remember that last time we gave name as the serial number 258, number as 259. For U minus, I am giving 260. So instead of writing U minus every time, I can write 260, and then also I can able to access that one. It's kind of aliasing. Right? Because here in the macro definition, I am defining U minus 260. So in all the occurrences during the pre-processing stage, in all the occurrences of the U minus, it will be replaced by 260. And what does 260 means or implies? So that is mentioned here. Okay. So the structure definition of the symbol table will be same. This is the content of the parser.h. Again, the flex specification will be same. Since ID I am writing pattern here, so the rule here is within curly brace ID. Otherwise, I can directly write this statement from here to here. Okay. Now let us go for the same sample round that we have done on the last class. It is a equals to 8 plus 9 slash n, a plus 4 slash n. So here it is, a equals to 8 plus 9, a plus 4. Now you see that now what I am doing, I am using ambiguous grammar. E derives E plus E, E derives E minus E, E derives E multiplied E, E derives E divided E. And also unary minus is of course there. Now if you, I am not going to explain step by step, you can work out this one, you can look at it, it's very easy. So just to tell you that it is top down approach, I am starting from L dollar. So first production rule is being used, ls slash n, then x is expanded to e, then e is expanded to e plus e. So like that way I finished the generation of the string. Now if I go for bottom up approach and use a stack for the evaluation, then you know that when I will encounter say a, okay, so when I will encounter a, then that a will be entered in the symbol table. But for right now or for this moment, I do not have the content of a. Okay. At the same time, this ID will be entered in the stack. And as an attribute, this ID will know that where this a is stored or the address of a. Because when finally assignment will take place, then the assignment will take place in that particular memory location. Okay. Next, num, actually that is 8. 8 is nothing but the num. Next, that num will be reduced to e here. Then shift addition is inserted. Then num, it is 9, num for 9. Then this num will again change to e. Now you see e plus e, and that will be evaluated to e. Its value is 17 now. Now id equals to e. With that, what I will get, that 17 will be assigned here, and 17 is assigned here. Okay. Okay. Let me use this part. Now this id equals to e will be reduced to s using this third production rule. Then this s will be reduced to l. We are not done yet. We have finished only this part. So to look for the second part, so a plus 4 slash n dollar. So a plus 4, so a is my identifier, so that will be inserted into the stack. So previously it was L, because here you see that this L was not popped out, and also that variable a. Okay. Now L is here. In the new line I got a. So a is reduced to, so a is nothing but the id. So I am having id here. Now you see that, you remember in our symbol table function, it was search and insert, or lookup. If doesn't exist, then insert. So when I will see a, last time when I see a, then at the symbol table there was no entry corresponding to a. That's why a entry was created. But this time a entry will not be created. So this a exists. So only id will be pushed to the stack. Next addition will come. So that will be pushed. Next another num, and that will come here. That is 4 is number. Now num will reduce to E and ID already reduced to E. So E plus E. So that will be E and that value is 21. Then E will be reduced to S, ls/n, that will be reduced to L. 21 will be printed, but it will not be stored. Same thing what we have done yesterday. Only thing is that now I am dealing with the ambiguous grammar. So there is ambiguity, and to deal with the ambiguity, I incorporated the precedence and the associativity information in my Bison program. Now another interesting fact regarding this ambiguity is some common confusions you create in your programming and data structure class. So you remember that if then else condition, right? So if there is some condition, else you will do something. Now there is a possibility that there is no else part, only if is there. And next there is another if, but that if has a else part. Or it can be opposite also. So what I am telling, so if else, this is one situation. Another situation, if it doesn't have any else part, another if, and then it has else. Another situation, if else, if else. So if it is the situation, then confusion you had in your mind during that time. That's why mostly I suggest for a proper indentation during writing your C program is that this else here binds with which if. In this case only one if is there, so it can bind here. In this case, whether this else will bind with this if or this else will bind with this if. That is the question. And this is very interesting and it is not very straightforward. If I do not use a curly brace, then it may be a mistake. Because you know, it may be the case that outer if, so this if has a else and it is this, and inside this if there is another if which does not have any else. That is possible. On the other hand, so this if does not have any else part, but the second if is outside or say maybe inside of the if, but it has some else part. So how to match that else and if? That is the ambiguity. And that ambiguity arises because so for this if else, my production rule will be statement derives if expression then statement else statement. So here if you look at the first one, then this bold and not italic indicates terminal symbol. So if is terminal, then is terminal, else is terminal, and expression and statement italic, those are the non-terminals. Okay. Now this is one situation, if then else. This is another situation, if then. And there may be some other statement also. Now if I write in short, instead of if I, instead of say then T, instead of else E, like that way, then I can have one grammar something like this. So this small I indicates terminal if, small e indicates terminal else, small I is terminal if, others is A, and this capital and italic S indicates some statement, one or multiple. For that production rule, I didn't write anything as of now. So there can be some other production rule also, and you can use only this one also, where say either it can be if else or if, and S can be terminated with this terminal A, that is my other. Now if I draw the state and the parsing table here, then I will find since E and dollar, so this E and dollar, that is the end of the string character, both are in the follow of S. S is the only non-terminal here. Hence, in state 4, we have shift reduce conflict. So, state 4. So, shift reduce conflict. On E, between, so when say my dot is here, so this is my one item and this is one item, then which one to choose? Shall I consider that it is part of if else? Or shall I say, no, it is part of if then else? Parsing or processing up to that if then statements, it is not possible to say that whether it has else part or not, unless otherwise you have a look ahead. Okay. So this kind of ambiguity also you can able to deal using Bison. So that's it regarding the parsing process. Now, if you have any question from this, please let me know. After this, we will go to module 5. That is the next module. So, do you have any question? Okay. Then let us take a small break of say 5 minutes before going to the next topic. Okay. So let us continue in this module. The module is mostly known as intermediate representation, but it includes a lot of things. So we name it as machine independent translation. So while we will do this, we will consider its existence after the parsing process and before the machine level code generation. So the module is completely independent of the machine, in which what is the language set for the machine, whether it is a x86 or not. So that we will not consider here. So the objective is to understand intermediate representations, symbol tables, understand syntax directed translation, in short STD, and understand how semantic actions by guided this syntactic analysis using attributed grammar. So it is the same thing, but more information will be injected to make it more meaningful. Because you know that, say you are writing one program, and when it is a C source program, then the parsing, the lexical analysis or the scanner is dividing the source program into tokens. Then it is the token string which is going to the parser, but the token string doesn't contain any meaning. So it is just looking at the patterns, whether those patterns are correct or not, and if yes, then it mentions that in which category this pattern or tokens falls. Next, during the parsing stage, we cross-check that whether the source program is following some CFG, the grammar, or not. And after that, we have to make some sense, and also we have to check that it is doing correctly. Then we can move on to the machine translation. So here is the outline, objective, then intermediate representation. Sometimes this is called as the IR, since it is intermediate representation. Sometimes it is called as the TAC, or 3 address code. So intermediate representation because it is in between the source program and the machine code. That's why intermediate. And why it is 3 address? Shortly I will go to that one. Then I will discuss in detail regarding the symbol table here with more examples. And then we will move on to translation. A lot of different translations are there: arithmetic, Boolean, control, types and declarations, use of type in translation, arrays in expression, type expression, function, scope management, and some additional stuff that we are planning to cover. Okay. In the intermediate representation, so each compiler uses 2-3 different intermediate representations. There are different levels of intermediate representations: high level, mid level, or sometimes it is called HIR, high level intermediate representation here, or MIR, mid level intermediate representation, etc. If I wish to understand that what is the basic difference between this high level and mid level, is that in high level it preserves loop structure and array bounds. Mostly it talks about the abstract syntax tree, or AST, and DAG. It is the condensed form of parse tree. It's useful for representing language constructs. It depicts the natural hierarchical structure of the source program. Each internal node represents an operator. Children of the nodes represent operands, and leaf nodes represent operands. Of course, DAG is more compact than AST because common sub-expressions are eliminated. So those things we will discuss in detail with examples. Here, just to give some features or properties of HIR and MIR. Compared to HIR, high-level intermediate representation, mid-level representation mostly looks for a range of features in a set of source languages, language independence, and it is good for code generation for a number of architectures. You remember this figure from our first class, and it is also taken from the Dragon book. It's a very simple expression evaluation starting from the source program expression, and finally I am having the machine language. So you can consider this is high level language and this is machine language. How I am proceeding and in which stage actually IR stands, just to demonstrate that one. So this is my source. So first it is the lexical analyzer who takes care about the source program, identifies the tokens or tokenize this and send it to the syntax analyzer. Syntax analyzer, with the help of its grammar, checks the correctness of the syntax. You remember we have drawn several parsing tables, and parsing table helps us to realize one string. In this case, this expression position equals to initial plus rate multiplied with 60. Whether that string is following the grammar or not, that is being tested during the syntax analysis of the parsing stage. If during the parsing process I do not hit any blank, the blank in the parsing table indicates that it is an error. If I do not hit, and after the expression, if I reach to accept state, then that string is accepted by that grammar. Next, I will try to put some live kind of thing to the program. So from this syntax tree here, syntax tree, you see how it is changing to the another tree after the semantic analysis. So the change here you see that multiplied with 60. Now whether that multiplication is going to be integer multiplication or floating point multiplication, that is kind of decided here, and the typecasting stuff here you see int to float is done at this semantic analysis stage. After that it comes intermediate code generator, where this code, as I mentioned, sometimes called as the IR or tree address code. Now this part is in between this high level language and machine level language. You see the only feature or property right now you can look at it is that these are very simple statements and only one operations, either say assignment here or binary addition, binary multiplication, or this say integer to floating point conversion. These simple expressions, and those actually combine to this high level language specification, where it is mentioned position equals to initial plus rate multiplied with 60. Now we will mostly focus on this and this part here in module 5. Okay. Then will come the machine independent code optimization. As of now, you see that we didn't consider the existence of any system. So this IR of tree address code is generated based upon the analyzing the input. Now after this, I will do some optimization. Then I will map it to some machine level code. So this optimization actually does in two steps. First, before the machine level code generation, then the optimization is machine independent code optimization. Another, after machine level code generation, then the optimization is a machine dependent code optimization. Okay, let us see. Here is example of some alternate intermediate representations. So this will be available, this slide. I'm not reading this one. You can have a look just for your knowledge. Let us move on to 3 address code. So the concept is that there will be address and instructions, and it uses up to 3 addresses in every instruction, right? So 3 addresses plus 1 opcode. In total, how many? 3 plus 1, 4. That is my quad. So that is the basic representation of a 3 address code. It suggests you break all the expressions into small pieces such that in each piece at most 1 opcode and 3 addresses are there. And of course, if I combine all those pieces, then it should evaluate the same expression from which I have broken this into small pieces. Otherwise, you know that there will be some logical mistake. So the program is telling something, and during the compilation, during the 3 address code generation, if you make some mistake, then it is the mistake with your compiler. So it is not compiling properly, and accordingly, the result will be different. Okay. So address are of several types. You are familiar with this name, that is my identifier or ID. This constant may be integer constant or floating point constant that we considered as num in my grammar. In addition to that, 2 more things will come. One is called as the computer generated temporary, another levels. So first, computer generated temporary. Let me go back to that slide. I'm going back. Here you see that initially it was position equals to initial plus rate multiplied with 60. Now I imposed one condition to you that you should not deal with more than 3 memory spaces or constant, and there will be at most 1 operator. Of course, in this case assignment I am not including. If it is so, then in order to evaluate this expression, first you need to do this multiplication, right? Now after doing this multiplication, you need to store that information to some memory location. Otherwise, how do you do that one? Right? So when, say, you are thinking of some tree structure like this and you are evaluating, then also you assume the existence of the internal nodes. Now these internal nodes are not declared as variable by the source program. So the source program only declares, say, position, initial and rate. Now you wish to multiply rate and rate with 60 and wish to store that information to some memory. that memory is extra or additional, and that memory is allocated by the compiler during the compilation process. That memory is that's why that memory is called as the compiler generated temporaries. Since those are temporaries, so usually those are written as T followed by some integer number. Now look, to be honest, I do not know when say I am compiling the source code that how many such temporaries will be required for me. That's why instead of declaring those variables at the beginning, I will declare only when there is a requirement. And if it is the case, then how do I manage the name of the variable? So one situation you may think of, say, as you have done in C programming language, that dynamically I will allocate the memory. But if it is not dynamically allocating the memory, another solution is that you assume that T is the first character followed by some integer value, and that integer value you keep on incrementing. And if you do that one, then you will get as many number of variable names as you want, and all are temporary variables generated by the compiler. So its scope, its life, its existence is as long as the compiler is compiling your source code. Once the compilation is done, it will generate the machine level language, then this time temporaries are not required. So those additional things will come here, and that is called as the compiler generated temporary. Those are usually named as T followed by some integer. Now you may think, and you are right if you're thinking, that if there is some user defined temporary, something like T, or say T1, if some user defined variable is T or T1, which is part of the source code, then there is a possibility that it will clash with the temporary compiler generated temporaries. Yes, I agree, completely agree with you. Then you may think that, okay, then I can give whether say underscore at the beginning or something else, so that it will not clash with some user defined temporary value. So when I say user defined temporary value, not temporary, user defined variable, then that user defined variable is part of the source code. But this is compiler generated temporaries, and it is generated during this 3 address code to store the partially computed result during the computation, right? Also, you will see one advantage. Again, I am going back to that side. When the expression is of this nature, say T2 equals to, I am erasing everything, say T3 equals to ID2 plus T2, then you see that there is this actually statement can directly be translated to some machine language. So I can write add ID2 T2, then these two will be added. So again, then I am finding some advantage of this 3 address code or IR, because the complex expressions are being broken into simple expressions, where corresponding to each such expression I can have one machine language code, so that my machine code generation will be very easy. It will be just you take one expression and you look for the corresponding machine language, copy that information, that's it. So that is also another advantage or purpose of breaking it into 3 address code. These labels are required because of the jump statement. the jump can be conditional or unconditional, because you know that when I will break, shortly I will break and I will show you the basic instructions for 3 address code. Then for loop, while loop, those loop will not exist. Instead, there will be a jump statement. So when it will be a jump, then it should jump to some level. So that level information is also required. Now let us look at that if I am interested to break the expressions or the statements into 3 address code, where the rule for the 3 address code I have defined that at most there will be 3 memory access and 1 operator or opcode. Then how many different variations of 3 address code exist? Let us look at that one. So instruction types for addresses X, Y, Z and level L, that I am assuming. Binary assignment instruction for a binary operation, including arithmetic, logical or bitwise. You can write X equal to Y of Z. You see how many memory access? Y, Z and X. How many opcode? Only 1. Now this opcode is a binary opcode or binary operator. That binary can be arithmetic, logical, bitwise, whatever it may be. When it is binary, what about the unary? Simple, X equals to op Y, that is my unary operation, and X equals to Y, simple copy statement. Okay, so these 3. So you can mark it 1, 2, 3. What else? Unconditional jump. Sometimes it is required. So go to L, because I assumed L. So it is my 4th. Since unconditional jump is there, so conditional must be there. In the conditional, there are 2 categories. One is value based, another is comparison based. So value based says that if this value is true, then go, or if this value is false, then go. Another is that you compare these 2 values, and if it is true, then go. Okay, so 3, so 1, 2 and 3. Now you may argue, and I agree, that this part Y rel of Y, that can be evaluated separately. That value can be stored, and then I can use either this value based this one or value based this one, if X or if else X false. So if say this can be written, say Z equals to X rel of Y. So previously I will calculate that one, I will have this Z and then use value based. I agree, you can do that one, but otherwise you can use this comparison based. So if I use comparison based, so 4, 5, 6, 7. As of now, 7 basic instruction types in 3 address code, and I am trying to break it into and cover it all the basic 3 address code, so that using a combination of them I can evaluate any expression or I can perform any operation. Okay, what next? Function call or procedure call. So procedure call, as you know, that this say integer function, then I am sending some parameters. In that case, it will be coded as parameter 1, parameter 2, parameter 3, like that you will say, and finally we will call Y. Y is the return. Call P, P is the name of the function, comma N, N indicates the number of parameters. And just before this, you mentioned who are going to be your parameters. So this number is 8 now. This is the function call. Now I believe you are not surprised by seeing this kind of function call, because we have seen this in assembly language program, where we loaded the parameters into the designated registers, and then finally we call the function. Now once the control is transferred to the function, then it will understand that from where to pick the parameters. And also here I am mentioning that how many parameters are there. Now regarding this parameter, so some compiler uses the convention that you will load x1 first, x2 next, then x3, like that up to xn. In some cases it is just opposite. So x1 first, then n minus n, then x2, finally x1. So either it will be like this or like this, based upon the convention of the compiler, and varies little. Okay. Note that n is not redundant, as procedure call can be nested. So this is important. Parameters may be stacked in the left to right or right to left. That's why I said that either I can write parameter x1, parameter x2, parameter xn, or I can write parameter xn minus 1, parameter x2, parameter x1. So either this way or this way I can pass the parameter. It depends. And whatever implementation you will do, you have to keep it constant. Now there cannot be any parameter also. That's why I am having it open n greater than equals to 0. Now the return value, returning a return value or an assignment is optional. You agree with me? You have seen that one, but that is my 9th, say, basic 3 address code, return n. Okay. Next is interesting, two things: the existence of the array and the pointer. So when it is array, then x equals to yi is my 3 address code. What is operator here? Operator here is to these two are the operators. Okay. So 10, 11. You are familiar with this assignment operation for the address and the pointer. 12, 13, 14. Probably that's it. Yes. Now the interesting point is that in your assignment 5, you have to write the 3 address code, and for that you need to use this basic 3 address codes only. Once that 3 address code generation is done in your assignment 5, assignment 6 is going to be directly from this 3 address code you translate to machine code. And in consultation with a lookup table where there is a mapping of 3 address code and the machine code, you do the mapping, you generate that. Interesting, right? But along with this 3 address code, you need to keep track of compiler generated temporary variables, right? So here is your first example of 3 address code. Code is very simple: do I equals to I plus 1 semicolon while ai less than v semicolon. If I break, then you can understand I plus 1 first I will evaluate and store in some t1. T1 is what? Compiler generated temporary. Then I am assigning this t1 to I. Next, for this ai, you know this I is the index, and in order to know that what is the memory address, so you have to multiply I by the size of the variable a, or the amount of memory space or the number of bytes it requires to store one value of variable type a. So that I am doing I multiplied with 8, assuming 8 bytes are required to store one variable. Let us assume long double is my data type for a. I am storing that to t2, and then a t2, now I am copying to t3. Next, my condition testing, if T3 less than V, it is same as from here. Then go to L. So you jump back here. You see, everything is now in 3 address code. Now the first part is written, it's fine, no problem. But you know, this particular say 3 address code will be mapped to some memory. It will be stored there. So if I give some positional number, so this is my first code 100, 101, 102, 103, 104. Then my go-to will be following that position, that is 100, not L. And mostly we'll be using these positional numbers. At this point, I would also like to inform you that when say I am compiling, I do not know that when the program will be in execution, which memory will be allocated to it, or what will be the address of that memory. I do not know. That's why what I will do during the code generation, 3 address code or any other code generation, that corresponding to each code, I will give some address and say that address will start from 0 without knowing anything. So that whenever some memory will be allocated to me by the operating system, during the loading process, what I will do, I will consider the initial address that is supplied to me as the base address and each positional number as my offset in order to load it into the system. Okay. Now, if I represented that in my words, how will it look like? So my opcode, the second column, first column is just the serial number. Opcode, argument 1, argument 2, result. For the first one, opcode is addition, argument 1 is I, argument 2 is 1, and result will be stored in T1. For the second one, my opcode is assignment, my argument 1 is T1, argument 2 is absent, so that's null, and result will be stored in I. Similar to that, for this one, opcode is multiplication, argument 1 is 8, argument 2 is argument 1 is I, argument 2 is 8, and the result will be stored to T2. For this one, opcode is equals to square bracket. So this equals to square bracket indicates that on the right hand side I have one array element. So array element means what? You know the base address is A. With that base address you have to add T2 in order to go to that location. From that location you pick that data and store it in T3. So everything, all the meaning of it is being stored when I write the opcode equals to with square bracket, open and close. Now what are my arguments? First argument is A, second argument is T2, and the result will be in T3. For this goto, what is my quad representation? So first argument is T3, second argument is V, and my opcode is less than, result is L. L is my level. So by looking at L is my level, it will understand that there is a goto statement. Or you instruct your compiler that it will translate, or it will actually explain that this is the goto statement. Okay. So up to this, do you have any question? 3 address code. Next we will go to the symbol table. Anybody has any question? Okay. Let us move on to the symbol table. Let us start with this simple C function. In this C function, you can see it is integer function. It is taking two parameters as input, integer x and integer y. Inside that function, I have two local variables declaration, ij, and its function is doing something, do something, and finally returning 0. Now you know that whenever I will encounter an identifier, so I need to store that information to symbol table. That we have discussed. The implementation of the symbol table also we have discussed in the Bison. We will look into it into more details. Say whenever I will see that this is x and this is y, then in my symbol table I will have an entry of x and y, and x and y are parameters. So I will have that information also, param, this is param. Next, what more information do you want? What is the data type? So I will have the data type, integer, integer. Next, I need to know that how much memory is required to store this variable. That information you got using size of operator. Now here I am mentioning say 4 bytes and 4 bytes. One more thing will come, I'll come to that, but let us see that up to this it is more or less okay. So x is the name of the variable, so it is a parameter, its data type is integer, and it is it will take 4 bytes for the storage. Y is also same. Now for I, this is a local variable, so I am writing local integer 4, j local integer 4. Now only one thing is missing, that indicates that what is the memory location for this variable. Now you know in your C program, when say you are defining or declaring some variable, during the runtime only you get the memory address, and if you run several times, there is no guarantee that always you will get the same address. It may vary, and I hope that is clear to you that why it is varying, because different time you are running, different operating system may allocate different memory location, and that's why you are getting different. Now at the compilation time, what will happen? At the compilation time, it will assume that this is your 0 as it, and instead of storing the actual address, it will store the offset. So here if it is 0, then I am moving down from here, I am storing moving down, and here I am moving, I am storing by moving up. So that offset information will be here. So then if it is 4, then it will be 8. If it is 4, then it will be 8. Now one will be negative, another will be positive. So it will be negative going down, and this is positive. Positive you can give or you cannot give. So that is going to be the structure of the symbol table as of now. More attribute information or other information will come. That is about the variable. What is about the name of the function? That information will also store in this symbol table. Also, how many symbol tables are there? Those questions I will answer next. So here is the notion and purpose. So it is a data structure that you have seen, and symbol table is used by both analysis and the synthesis part of the compiler. It is said that usually the symbol table is constructed during the lexical analysis and the parsing stage, and being used for the say IR and for the machine code generation, code optimization, so for this thing. Okay. Now a symbol table may serve the several purposes depending upon the language: to store the names of all entities in the structure form in one place, to verify if a variable has been declared, to implement type checking by implementing assignment and expressions, to determine the scope or name. So those things I will discuss when I will take little more complicated example of source program and will draw the symbol table for it. Okay. So different steps of the compiler actually uses the symbol table. Here is the diagram. It is better to understand from here. So lexical analyzer, so it is kind of a one way. So symbol table is not asking for anything from the so symbol table is not sending any information to the lexical analyzer. Whenever it finds some identified token type, it sends that information to the symbol table for the storage. Now the syntax analysis stage, it is both way. So it is if something is missed out at that lexical analyzer, so those information is added. At the same time, it is going for a lookup. So whenever say one variable identifier or integer constant I have got, so I am checking whether it exists in the symbol table. If yes, then it returns the address. If no, then it will make an entry to the symbol table. But for the semantic analysis and the code generation, again it is one way. So only the symbol table is being used there. So the symbol table is mostly populated during the lexical analysis and parsing stage and being used by the semantic analysis and the code generation stage. So what can be the entries in the symbol table? Various information it can store. So first, of course, is the name. It will be stored as a string. Name may be quantified for scope or overload information. Since it's a name, so it can also store the integer constants also. Data type, explicit or pointer or to type to table. Block level information. So when you are declaring one variable, so what is the scope? How much memory is required? What is their initial value? What is the offset from the base pointer? That base pointer, I have drawn the horizontal line with 0. So those information it will store. Along with that one, it will keep an eye that whether it's a variable or it's a name of a function, whether or it's a constant, and whether it's a structure, union, class, namespace, all those information it will store. So I will explain one after another. So I believe that you have a clear concept of scope and visibility of a variable within which its life and the visibility is there. So those are classified in statement block, method body, class body, module, package or file, or the whole program. So which one is valid? Whose scope and visibility is valid for the whole program? It is the global variables. Otherwise, it's local. Okay. So those things I will discuss. Global scope, class scope, method scope, code block scope, variable defined inside a block. So those things will come. What are the interfaces? Up to the Bison implementations, we have seen the interface includes the lookup. That lookup includes search, and if it is unsuccessful search, then insert. So this one. But you can separately have insert and lookup. That is up to you. If symbol table is not there, then you need to create. Now please note it down that symbol table, there are a number of symbol tables. It is not only one symbol table. Why I am calling a number of symbol tables? Shortly you will understand that one. And of course the update attribute. So if you get any extra information regarding that variable, go on and update. One prime example just today we discussed is that, so when you are evaluating some expression, so the production rule is ID equals to E. So that expression will be assigned to the identifier. Assigned to where? To that symbol table. To that memory location it will be. So that update the attribute. So those are the interfaces. And how do I implement the symbol table? So either linear list or hash table or binary search tree. So you know from the class of your algorithm that what are the advantage and disadvantages of this. So I'm not going into details. So from time, from space point of view, what are the advantages? You know that one. And you can choose to select either linear list or hash table or binary search tree for the implementation of your symbol table. Now here is a full scale example of program. So first you look at this left hand side program. It is very simple program. If you start with main, int main argc character argv here, then there are local variables integer x2 equals to -2 comma y2 equals to 3 comma dist equals to 0 semicolon, or all are integer variables. Then dist equals to, I am calling the function m underscore dist and passing the arguments x1 x2 x1 y1 x2 y2. Now x2 and y2 is local variable, whereas x1 and y1 are global variables. Integer x1 equals to 0 comma y1 equals to 0, so those are also 0. And finally main is returning 0. Now looking at the function mdist, int mdist, integer x, integer y, integer x2, integer x1, integer y1, integer x2, integer y2, 4 parameters are there. 3 local variables are there, integer d, x difference, y difference, and the statement is x difference is x1 greater than x2, then x1 minus x2, x2 minus x1. So those expressions are here. Finally d equals to x difference plus y difference, return d. So it is basically calculating the Manhattan distance. Okay, so taking the difference of x and y and then adding the difference in order to get the final distance. Excuse me. Now, if I go to the tree address code that we discussed just now, then you see that m distance that for that function. So what I am doing? So regarding the declaration, I do not have to do anything for the tree address code generation. Directly, I am starting with x1 greater than x2. If x1 greater than x2, go to L1. So I will move to L1. If it is false, then, so if it is false, I know that it will execute x2 minus x1. So I am computing x2 minus x1 and storing that to temporary variable, compiler generated temporary variable t1. After that one, I am jumping and going to L2 to avoid my L1, where L1 is going to evaluate x1 minus x2 and will store in the temporary variable t1. Now you see, in both the cases, I am using a compiler generated temporary variable t1. Reason is that the operation will be mutually exclusive. Either x2 minus x1 will be evaluated or x1 minus x2 will be evaluated. And in go to L2, so x difference is t1. So t1, which is x difference, that I computed and stored. Similar to that, for y difference also, I can write that one, and that y difference will be stored in t2. So I computed x difference and y difference. Now I can compute d equals to x difference plus y difference. Finally, I will return d. Simple tree address code. Now for the rest of the program, so I am not interested in tree address code. I am not interested in variable declaration, but here in the global declaration, assignment is also there. That's why here I am writing x underscore g equals to 0, y underscore g equals to 0. This underscore g is to differentiate the global variable from other x1 variable because it's part of the 3 address code. If I do not differentiate, then I may misinterpret. That's why I am giving a marking. So underscore g for global variables to differentiate this x1 from the x1 which are passed as a parameter to mdist. For mdist, I didn't give any prefix or suffix, but for this x1 and y1 as a global variable, I am giving underscore g. Now in the function main, so x2 is assigned to -2, y2 is assigned to 3, and dist equals to 0. That I have done. Next, I am planning to call mdist. Now you remember 3 address code. Before the call, you should load the parameter. So I am loading the parameter. So it is, you see that I mentioned in the parameter either it can be left to right or right to left based upon the kind of language or say compiler you are writing. Here it is right to left. So parameter y2, parameter x2, parameter y1 underscore g, because this is the global variable, parameter y1 underscore g. Then I am calling the function dist equals to call mdist, comma 4 indicates the number of parameters. Finally returns it. Any question up to this? This 3 address code generation from this source code here to here. Good. Now we are trying to construct the symbol table. So first of all, have you ever thought that whenever say variable name is same, but one variable is say occurring in function main, another variable is occurring in say other function, then how does the compiler differentiate between these two names? One is inside the function main, another is inside say function foo or function fun. So how does this differentiate? Also, more interesting feature, inside a function, say function main, I am declaring one variable as a local one. Again, inside a say for loop or just simply inside a opening and closing brace, if I declare another, if I declare the same variable, then inside that block or that for loop, its behavior, I mean its value assignment, if I print, then that is different than the local variable, right? So from the top level, when we are doing the programming, then we may think that how does it able to differentiate between these two situations where the name of the variable is same, but their values, I mean their scope is different, their accessibility is different. How do they manage? They manage simply by having separate symbol table corresponding to each function, each block. Okay. So first of all, to include all the global variables, including the global function declaration and definition, it will have one global symbol table. The name is st.glb, the first one. The global symbol table, this one. Who is the parent of this global symbol table? Null, nobody. It is global. Who is its parent? Nobody. Now what is inside this one? The first one, let us skip for the time being. I will come back. x1g is my global variable. I mentioned variable name, its data type int, then its scope, that is global. What is the number of bytes required? 4 bytes. y1 underscore g, then its data type integer, its scope is also global, and it is of 4 bytes. Okay, two variables done. Now two function declaration, int main and int mdist, are also global. So the name of those functions I will store here mdist and main. Now interestingly, what will be its data type? Very simple. You look at the number of parameters and their data type. So for mdist, there are 4 integer parameters. So int cross int cross int cross int maps to int. So the second last int indicating the return data type, that is int, and 4 other cross indicates that those are the parameters. So if it is so, then for main what will happen? So int argc, so int cross star argv square bracket, so 2-dimensional array it is. So array within parenthesis star comma character star maps to integer, return type is integer. Now of course this is global, but its type is actually, it is function. So I am writing function. And how much memory is required for this one? 0. Nothing is required. For the declaration, nothing is required. Okay. Now you see that when I declare the variable, then immediately, I mean not immediately, when say I am parsing that one, then I am scanning that one and then parsing, then corresponding entry will be there in the symbol table. Now if say you are defining one variable, one function which will take 4 integers as an argument, but actually during the function call you are passing 2 or so, then you have seen that it is telling you that it is not matching, the parameters are not matching. From where it is getting that? Very simple, from here, from the symbol table you mentioned integer cross integer cross integer cross integer. Now if you pass 3 or 5 or something different than 4, then it will not be able to match. Then it will assume that you are probably calling some different function, not this function. And if that different function exists, then you are actually vouching for the existence of an overloaded function. So it has different meaning. Okay. Now that is about the global one. Similar to that, corresponding to each function, there will be one symbol table. So I have one st.main for corresponding to main function, whose parent is st.global, and inside that one who are there? So parameters, argument, it will take 4 bytes, argc, parameter, integer, it will take 4, x2 integer local variable, y2 integer local variable 4 bytes, distance integer local variable 4 bytes. And you see that between the argument or the between the parameters and the local variables there is a vertical line, that is my reference 0. So parameters are above and it is increasing +4 +8. So it is increasing by this offset, and here it is decreasing -4 -8 -12. Okay. Now for mdist, similar to this. So first I will have the parameters. Again right to left I am using. So y2 first, then x2, then y1, then x1, all those parameters. And since those are parameters, so vertical line is here. Horizontal line is here. That is my zero crossing line. You can consider local variables d, xdiff and ydif, d, xdiff and ydif. And during the 3 address port generation, I generated T1 and T2. So those two will also come, T1 and T2. Now you see the type x1, x2, y1, y2, those are parameters here. D, xdiff, ydif, those are the local variables. T1 and T2 are temporary variables. Since all are integers, so all are of size 4. And here is the offset corresponding to that. Clear? Do you have any question here? Okay. Then next go to the next example. In this example, so what is done is that, so static allocation x1g and y1g, that is marked as green. It is done. Now, additional thing you probably noted here, I gave one brace extra. Here I gave one brace extra and both are closing at this position. Now, as you know, because of the existence of those braces, it will create a separate scope. So the variables integer x diff, x underscore diff, and integer y underscore diff, which are actually inside that opening and closing brace, I would say that a block, inside that block will have the meaning inside that block. So corresponding to that, two more symbol table is required to create, and I am creating here. So stm underscore dist dot $1 dot $2, along with the existing one, whatever was there, it will be here, but I am creating two more. Okay. And inside that one, I am declaring that x diff and y diff. And who is the parent of this? To st.mdist. Also, I am making this to embedded automatic allocation inside the mdist. Now, please note it down that because of this incorporation of the two blocks by this opening and closing brace, we are not making any change to the 3 address code. Do we? Yes, we do, here and here. Because now you know the meaning of that x diff and y diff has changed, and following the symbol table information, I am generating that one. So when I am generating that one, following that, then you understand that why it will be different when it is inside a block and outside the block. Say, along with this x diff which is inside the block, if you have another declaration of x diff outside the block, then along with these two red colored x diff and y diff here, one more x diff with black color will be placed here. Now, as long as I am inside the block, then my 3 address code will take the identifier x underscore diff underscore $2. But if I am outside, then it will pick x underscore diff. And that way, the value will change. That way, the value will change. Okay. So, few more examples are here. Say, when I am having one structure definition, it is the same program. Only thing is that instead of 4 integers, now I have one structure definition, structure of a point. Point means it will be x and y, which means that mdist will now consider point P and point Q as an argument instead of x1, y1, x2, y2, and accordingly the comparison statement and all those statements will change because it will be structure dot underscore x, structure dot underscore y. Now my global variable is also point P00, that is origin. It was previously also x equals to 0, y equals to 0. Now point Q I am declaring like this. So according to this, the 3 address code will also change. the name of the variables all will change here. Okay, and more interesting change will be in the symbol table. So in the symbol table, mdist and main, it will be there, but their arguments is instead of int cross int cross int cross int maps to int, it is now structure point cross struct point maps to int for mdist. For main it will be same, there is no change actually. Unfortunately I missed argc argv here. So here you please read, the argument is argc argv, otherwise it will be just void. Okay, void maps to int, otherwise it will be. So you please read here argc argv. Now the struct point is the only global variable now here, and what is its data type? Its structure, and how much memory is required for this purpose? 2 integers inside this one, so 4 plus 4, so 8. Okay. Now accordingly, if for mdist symbol table, so parameters struct point, that is the data type p and q, so right to left, so q and p will be here, those are parameters, size is 8 and 8. Then other d, x, t, yd, t1, t2 will be there. So t1 and t2 is coming from this 3 address code generation, temporary one, and that's why you see it is coming last, because first argument, then as I proceed, I am exploring new local variables, I am entering that one, and then when I see the 3 address code, then I am basically entering that information also. Now along with that one, main is fine, main is there, and one q struct point information is there. Now one more symbol table is required whose parent is global, that will keep the information of the struct. So x integer, y integer, it is the member of the struct data structure, and size is 4 and size is 4. So that is required, and that is here. Now if I have this kind of modification for structure, then definitely for the class also I will have similar kind of modifications. So here class definition, class point public colon integer x y point x point integer x integer y. So the function definition I am giving here. Corresponding to that, it is my 3 address code. Okay, so the function call is here. Now since only one argument is here, so that the constructor, this is the destructor. Okay, so this is here, and what will be the change in the symbol table? So instead of struct point, it is now class point, it is now class point, it is now class point, class point, class point, and here it is class point. Now the point will be integer cross integer maps to point, because this constructor here, integer cross integer, 2 arguments, and they are mapping to class point. And the destructor, it is the class point star which maps to void, so nothing is returned. So that is method. These 2 are methods, and these 2 are members for the C++ case. Okay, so let us stop here. If you have any question, please let me know. Otherwise, let us stop here. So next we will meet on Thursday, the test. So class test will start at 2 to 3 p.m. is the class test. It's scheduled on Thursday 9th. I will send an email also. And after that, there will be a break of half an hour from 3:30 to 4:30. There will be a lab quiz. So back to back with a gap of half an hour. Okay. And regarding the syllabus, I have mentioned, so it is up to the parsing. It is uploaded already in the Moodle for the theory, and for the laboratory, it is the assignment 1, assignment 2, and the scanner part that we have covered in the theory class, and lecture slides are also uploaded. Okay. Okay. So if you have any question, it's fine. Otherwise, we can stop here. Okay, thank you.